Euler's method is used to approximate solutions to complicated differential equations, as many differential equations are very complicated to solve. The premise of Euler's method is to use a differential equation and an initial value to find any desired y value by assuming that in between each step size, the gradient remains the same. We will then find every y value for each step size. The difference between a y value and the previous y value is the step size multiplied by the gradient at the previous y value. The smaller the chosen step size, the more accurate the approximation will be. As seen in the graph, the blue line represents the actual solution, and while we are unable to obtain the actual solution, we are able to approximate it using Euler's method as seen by the line drawn in pencil. The way to derive the formula is by using the previous value of y and the previous value of x to find the gradient, multiplying it by the step size, and adding it upon the previous value of y. Hence, the formula is yn equals to yn minus 1 plus the step size multiplied by the gradient, plugging in the values of xn minus 1 and yn minus 1. To solve the initial value problem, we must first fill in a table. For example, we have a differential equation of dy dx equals to x over y squared and a value of y bracket to 0 equals to 1. This means that our starting value is x equals to 0, y equals to 1. Now we are tasked to find y bracket 1, which is the value of y when x equals to 1. We will now choose step size of 0.2, meaning that x will increase in increments of 0.2 from 0, 2.2, 2.4, 2.6, 2.8, and then to 1. By using the formula that we have found in the previous slide, we can obtain the y value of each step size and apply it accordingly, and then eventually we can find y bracket to 1. Hence, by applying the formula, y bracket 1 can be obtained using this equation. Y equals to 1.210 plus 0.2, which is the step size, multiplied by 0.8 over 1.31 squared, giving you the value of 1.320. By applying the formula to each x value, we eventually arrive at the answer 1 equals to 1.320. As you may recall, using Euler's method gives us a y value that is close to but not identical to the actual y value. To obtain the y value, we will have to solve it mathematically. Given that dy dx equals to x over y squared, it can be solved as a separable differential equation by separating the x and the y, and then integrating both sides, giving you an equation of y cubed equals to 3 over 2 x squared plus c. Now we can find the value of c by plugging in the initial values of x equals to 0 and y equals to 1, giving us a c equals to 1. Now that we have the equation, we can find the value of y bracket 1. By plugging in the values, y bracket 1 is actually 1.357 compared to the approximated value of 1.320. Hence, we can see that there's an approximation error of 0.037 after you take the actual value of y minusing off the estimated value of y.